So we have studied about the basic arithmetic on the p-adic numbers, p-adic integers, and even considered p-adic rational numbers and some properties. Next thing we, of course, study is this square root. Decided to hide the half of it. So let's consider square root, and let's review things about the real numbers. And we know the square root of a exists in the real numbers if a is positive. So something like that is going on. Its only thing is that p-adic numbers, like the real number, is kind of completed all the way to the depth of the metric we're looking at, but it still has this integer structure. So there's this irreducible, so you can't really break it into half pieces if you consider here. So that's why we have a condition that if you want to consider the square root of this number, you must have even power on that side. But the rest of the part, the unit, has a very nice condition, something like this. So like half of the numbers has square root of a, and the other half of the number, negative number, does not have a square root. So something like that is happening. So I described it like this. If this unit is a square, we call it a quadratic residue, square in the mod p level, then this is going to be it's going to have a square root in p-adic numbers. It's easier to explain with this example. For example, p equals 5, and I'm considering these number without even the power p power part. That's quite clear that you must have an even power. So let's just focus on a being just a unit here. So for example 1, if this u is 1 mod 5, for example, then this x squared congruent to 1 mod 5 is solvable. It's because we have 1 here, 1 is congruent to 1 mod 4, and 2, and even we can have, in this case, negative 4, not negative 4. 4 mod 5, if you consider 4 in here, then if you square it, it's 16, so it's equal to the 1 mod 4. So we have actually two solutions in mod p level. So if you unit u, may have infinite digit, but if it is congruent to 1 or 4 mod 5, then it's guaranteed to be solvable. Not in this mod p level, but in the zp. This root 6, for example, that's a unit. That's your 6 here, u is 6, and it is congruent to 1 mod 5, and this one here is congruent to 4 mod 5. This is 1 mod 5 again. So if these is congruent to 1 or 4, you know it's solvable. This mod p quadratic equation is solvable. It is actually solvable in zp. So you'll be able to we'll compute square root 6, and from there you probably understand why that this part in here is the key. But if you look at this number 8, so that's our unit, but it is not congruent to 1 or 4 mod 5. This is actually congruent to 3, and this is congruent to 2 mod 5. So these integers do not have a square root in it, in the zp. So in this part I would like to introduce how to actually compute the root 6. 6's unit is 1 mod 5, so 1 is quadratic residue, x squared congruent to 1 mod 5 is solvable. But root 6 is not identified as within the Q. You remember a lot of Q's are actually identified in here. So there won't be a number whose square is 6 in the Q. So if the p-adic expansion has repeated digits, periodic, then it must be identified in here in a Q. But Q doesn't have root 6, therefore even in the p-adic integers, we know that root 6 that we're looking for is not periodic. So this term irrational has the same meaning in here. So how we're going to do it here is that we're going to find a 1 digit at a time. So if you happen to have n digit, it's actually n plus 1 digit if we have correct digit up to p to the n, and use that information, we're going to figure out what could be the next correct digit. So we use this root 6 notation, but what this really means is a number whose square is 6. So we're looking at this xn. This is kind of approximation up to the p to the n plus nth power. So if this is a number that we're looking for, it must have the property that its square must be approximately 6. So you can interpret this congruent symbol as approximate in this arithmetic sense. So we have this property, and then we're looking for the next digit, so we have to raise the level to the n plus second power. Then we have to add one more coefficient. If it is n plus first power, this was a 0, so as we raise it, we have a room to fit in another next level of digits. So we're looking for a number with one more digit whose square is 6. So if we can figure out the b that satisfies this congruence relation, and that'll be it. Let's see how we can do this. And of course, I'm gonna expand this square part, this binomial expansion of the second power. So we have these 3 terms squared, and 2 times these this xn and b times p to the n plus 1. If you look at this 2n plus 1, this is already pretty big enough. If you compare these two, n plus 2 and 2n plus 1, then 2n plus 1, 2 times n plus 1 is always greater than or equal to n plus 2 as long as n is greater than or equal to 0. So this is already 0 because the power is high. Then we're solving this one for b, so I'm going to isolate it here. So I'm going to move this xn squared to the other side. So it looks like this. So what do we know about 6 minus xn squared? We know the 6 minus xn squared is congruent to mod each other, mod p to the n plus 1. That means if you subtract these two, and this thing is going to start from p to the n plus 1. So that 6 minus xn squared has the same coefficient up to p to the n. So if you subtract it, it starts from p to the n plus 1. Whatever, if you factor it out, you will have a p-adic integer, beta in here. And this one here is copied on the right side. So I move these two terms that we're looking at with the beta in it to the one side and factor out the common factor p to the n plus 1. So you look at this equation here. This is supposed to be congruent to 0 mod p to the n plus 2. We already have p to the n plus 1, so this must start from p power, so that altogether has p to the n plus 2 power in there. Here we can use the fact that the unique factorization property of the p-adic integers is divisible by p to the n plus 2, and it needs p in that. So we can separate it like this. Beta minus 2bxn must be divisible by p, must start from p to the first, and the very first coefficient of this integer must be 0. Now, since this is a mod p, we can replace this complicated long number with the first coefficient. Everything that starts from p is going to be treated as a 0 since it's mod p. So the very first coefficient is denoted by beta 0, and the very first coefficient xn was a0, so we use this a0 here. And b was this additional coefficient we're looking for. So we got down to this level, which all requires just pretty much this a0, and beta 0 came from this number here, the 6 minus xn squared. So this has a lot of information. This uses a lot of coefficient in there. But this part only depends on a0, the very first coefficient. To solve this congruence relation for b, we can organize like this. 2b times a0 is congruent to beta 0. And if I have a multiplicative inverse of a0 by multiplying it, and we can get to this level. So it's actually 2 and a0. So as long as 2 is a unit and a0 is a unit, and if these are not divisible by p, then we can have a multiplicative inverse. That was the fundamental theorem for principal ideal domains. So at this part, it breaks down if we're looking at mod 2. So we have to use a different technique. It's essentially the same technique. We just have to look at more digits than just A0. You have to look at a block of 2 or 3 digits to guarantee that it has a starting point, and then we can extend this technique still. But if p is greater than 2 prime, then 2 is going to be obviously not divisible by p. A0, in our condition, we consider the unit, so the very first level of a solution is going to be a unit solution because we start from the square root of a unit, so that's guaranteed to be a unit. So this is solvable, and it's pretty much a unique solution. It's actually a unique solution in between 0 and mod p. So when you try to lift it to the next level, you don't have many choices. You have one and only one choice of a b that makes this congruence work. So let me summarize it here. If you have xn, its congruence level up to p to the n plus 1 is correct, then xn plus 1 is its p-adic approximation up to the p to the n plus 1. This an plus 1 is determined by that equation, that beta n2 b and a0, so that was a b here, and this part was a beta after you knock down p to the n plus 1 from 6 minus xn squared. So that's a beta part, and you divide it. Rather, we should use this 2a0 inverse, but I prefer this form for the next part, to initiate the next part. So this is the recursive algorithm. You have xn, so how do you find the next digit next to coefficient, and you go through this formula, and this is always solvable. The solvability of this one, again, depending on this a0 being unit and 2 being not divisible by this prime p. So if you look at the very first condition, if you look at mod p level here, the a0 squared congruent to 6 mod p should be solvable, and because it's 1 mod 5, we know it's solvable. For all the rest of the coefficient, we have a unique choice like this, but at the beginning we have two choices actually. A0 can be 1, but A0 can be 4. If you square 4, 16 is still 1 mod 4. So there are two choices. Just like plus minus square root, we have two choices at the beginning. We have two choices. Once you fix that A0, and rest of the coefficient is completely determined by this formula. So that's how you compute root 6 in the p-adic number, and when p is 5. This pretty much explains in general how to compute root of a unit when it's solvable and p is greater than 2. So I'm showing you the summary of computing the p-adic integers approximation of a square root 6 when p equals 5. I'm going to slightly reorganize this by just changing this to xn squared minus 6 and changing that to xn. Then it looks like this. Xn plus 1, it's simply adding this one more number, one more coefficient as an plus 1 and p to the n plus 1, and an plus 1 is computed this way where it was before 6 minus xn squared. Now I pull out the negative, I wrote it like this. So I wrote it like this to trigger you think that this looks a lot like Newton's method. Newton's method is xn plus 1 equals xn minus this number. If you replace this one with the equal symbol, it looks a lot like Newton's method. So the question is that will Newton's method will work for this one? So we're going to try what happened. So Newton's method is that just if you're looking for root 6, we look at the function x squared minus 6 and divide it by its derivative, and you subtract from earlier sequence, a term in the sequence, xn minus that, then it's xn plus 1. That's how the Newton's method works. Proof of this Newton's method becomes more straightforward when you look at this expansion. It's called a Taylor expansion, or polynomial case. You don't need the fancy Taylor expansion. You just simply divide this polynomial by x minus n, that's the remainder, and this is supposed to be the quotient. When we knock out 1 power of x minus xn, you divide that quotient again by x minus xn, and that's supposed to be the remainder, and so on. So you can get this equation by just repeatedly using the long division algorithm. Anyway, if you have xn, you can rewrite this polynomial with x and x there in terms of xn like this, centered around xn like this. And this really helps us to understand what is happening to this recursive equation. So this is the magic part, and if you plug in x equals alpha there, so alpha goes in there, that makes this one exactly 0. That was just doesn't have x in it. X equals alpha goes there, and alpha goes there. Since this part has xn squared minus 6 divided by 2n, and we're going to divide everything by 2n, first we move this these two terms to the one side, and leaving that alpha minus xn squared on that side, and I divide both sides by 2xn. So this one's cancelled, and 2xn goes to denominator. So that part appeared right there, and xn together with xn and minus this quotient becomes xn plus 1. So here these two terms becomes xn plus 1 minus alpha equals 1 over 2xn times alpha minus xn squared. So what this tells us is that how close this xn to our target alpha is determining how close the next number, xn plus 1, is going to be close to alpha. In p-adic integer, we have a very, very clean result. And another thing before I move on to introduce this, what is happening to our approximation in p-adic sense, before we do that, I'd like to point out that the convergence of this Newton's method usually introduced in a calculus, one variable calculus level, by looking at the picture and drawing the tangent line. That's how it started, but there is just more algebraic and straightforward explanation of what's happening to this approximation. How close is this compared to the next number? Something like that. And you can really use this idea to explain the convergence in the real line as well. But let's take this one into p-adic world and see if we can get something out of it. So here's a conclusion. We know this xn by looking at the first few digits. It starts from, for example, a0 here is 1. We know it's a unit. It starts from unit non-zero coefficients. So this doesn't have p power in it. So if alpha is already, xn is already close to alpha, let's say it has many digits correct, so it's up to p to the m, so it has, that means first m coefficients are correct. Then that part doesn't have any p power, so only this one has the p to the m, at least is a p to the m. If you raise the second power, and of course this one gets the p to the 2m, so this side here is divisible by p to the 2m. What that means is that the coefficient of xn plus 1 is already have this 2m coefficient digits correct. So if xn has m digits correct, and xn plus 1 will have 2m digits correct. And this is the same phenomenon. It's Newton's method in the real line. So here's an example. I actually start from 1. That's the first digit. It's congruent to mod 6 if you square it. Then it has one correct digit. If you run this algorithm, Newton's method, it's guaranteed that it's going to have 2 digits correct, because 2 times it always. Once you have 2 digits correct, it's going to have 4 digits correct. If you run this Newton's method one more time, it's going to have 8 digits correct. So go all the way from 0 to 7 and so on. So this is a pretty interesting phenomenon, just like Newton's method in the real line. So here's Mr. Isaac Newton. He probably didn't think about this p-adic numbers, but his method still works for p-adic numbers. Here's another interesting point. We start from 1. We repeat this recursive relation over and over. When you use computer to calculate this, we usually focus on a decimal approximation on that one. But let's do this calculation exactly. 1 goes there and go through this algorithm. You can easily see that wherever you are, is going to be always giant rational integer divided by another giant rational integers. So it's Rn(Qn) is a quotient of two rational integers like this. And the surprising part is it is true that this number approaches root 6 in the real line, just like Newton's were thinking. And we just showed that xn, this number, the giant two numbers divided, the quotient of this giant two integers, actually approach root 6 in the p-adic numbers as well. So we have an approximation of the real number that approximates this number in both field with a completely different nature. So the following is the explanation. This quotient, xn, if you look at this as a square version, xn squared minus 6, approaching r in the real line, that means if you write this real number, the rational numbers, into this form, this part with no p in it, and you factor out all the prime powers of a p, then if you compare this tn times p to the mn, the Sn is a lot bigger, so that eventually this becomes a lot bigger number, so that it approaches 0 in the real line. But in the p-adic sense, it only counts the prime powers, so no matter what happened here, this mn eventually approaches infinity. Therefore, in p-adic number is considered as a number that's close to 0. Here's what I got when I run the computer software 5 times and got this x5 in Newton's method in this exact form. So when I factor out those two integers, it turned out like this after some cancellation, I think. This is probably already reduced form, so the numerator appeared to be 5 to the 32. So the 5 times we started from 1, that kind of makes sense. So this 32 is exactly 2 to the 5th, right? So we have this much of a correct p-adic digits. And the denominator, you can see this huge. It's not easy to compare yet, that if this is actually bigger than this one, but if you add all this exponent, maybe it's still less than 32, but bases are pretty big. So as a real number, it seems like it's a pretty small number. And as a p-adic number, because of this high power of 5, is also a small number. So here are those 5 numbers. This is x1, x2, x3, and x4, and x5 under the Newton's method in the rational form. And I actually converted this x5 into decimal numbers. So that's what you get in the first number. And this is, I asked Mathematica to compute a root 6 in the real line, correct digit up to down to 31. So if you compare these two digits, it's up to here that's correct, and it's getting incorrect digit at this point. The fifth, the phenomenon of doubling correct digits is the same for the real line. The reason is not having too many correct digits is that our initial value, the 1, is kind of way off from the root 6, and that's what's the problem. But that was a right choice for the p-adic numbers. But it's not so good choice for root 6, but it's guaranteed that it eventually approaches. So if you do a few more, it'll double the correct digits even in this real line as well. But because of the start was way off from this is more than 2, that's why at this 5th iteration it's not showing us too many correct digits. But this is what happened to the p-adic case, and here this is x1, as I guarantee that at least 2 of them are correct digits, and there's 4 are correct digits. Next time you double it all the time, I'm sure this whole thing is now at this stage x5 is the correct digits here. Here in this slide, I'm showing the verification of what we got is actually correct. So in this part, I'm showing you down to the 50 digits of this x5. x5 was the rational number, and I converted to a p-adic numbers. p-adic integers down to 50 digits. And what I do next part here, I multiply actually this number and p-adic number to itself. That will be squaring it and showing it up to 31 digit. And this is the result here. So you can see this is 1 and this is 1 times p. So if you add this thing, you get 6. And all the zeros in here. In the next line, I'm showing you one more digit after you multiply it. And you can see it pick up one more digit here, but it's not 0, therefore it's getting a wrong result. But in the next 6, and you will clear this one out all the way further to more and more digits. So this is checking our approximation up to 31 digits is showing us that it's correct. Now let us think about those roots that we can consider here, but that does not they don't exist in ZP or QP when p equals 5. So 2 and 3, and 7 is 2 mod 5, and 8 is 3 mod 5. So according to that criterion, it doesn't exist. If you think about how we solve for square root, the very beginning, the a0, we cannot find a0 from 0 to 4, anything that whose square that matches this one. So that's kind of a proof that it does not exist in the QP. And let's think about that root of a -1 that didn't exist in the real numbers. And what we did is we created a number, imaginary number I, whose square is -1. And then we created a whole extended number system called complex numbers. We can do the same thing for QP and think about some imaginary number for p-adic numbers whose square is square is 2. And what we did with this imaginary number I is we just have to define how this interact arithmetically with real numbers. So this is how we actually do that in complex numbers. Instead of I, imaginary number, we have this omega, and introduce how we could add this multiply with the real numbers. And this is how we add these two numbers. And how we multiply. When we multiply, just use the distribution law. When we multiply these two, this w omega squared becomes 2. That's why you see this 2bd. And you use the same conjugate trick. C plus t omega times c minus t omega is a c squared minus omega squared is 2 minus 2d squared. And you can see these are just integers, p-adic integers. So if you can reorganize this whole thing into this form a plus b and omega, where a and b are p-adic rational numbers. Interesting phenomenon, actually very, very interesting phenomenon that happened with this imaginary number is that R was number system we get out of kind of completing to the depth of this decimal expansion, and the root of -1 did not exist. We threw in, we created these complex numbers, and surprising thing is this complete part, it is still complete if you look at each of the part, and we have this still completeness, but the surprising part is we throw in I just to take care of some quadratic equations that's not solvable in real line, but it took care of all the polynomial, not just a quadratic polynomial. So this is called the fundamental theorem of algebra. All polynomial completely factor in this number system. Everything has a solution. Although we learn this as some simple fact in our education, but it has a hard history. Look at these big names in the history of mathematics. At the beginning, they were trying to think about completely factoring all the polynomial with a real coefficient down to linear times a quadratic, and their attempt actually tacitly used the existence of a complex solution. So that's pretty much fundamental theorem of algebra, so it was incomplete. And in 1798 and 1799, these two people, the Gauss is another big name, attempted the proof, but they have gaps. It means it's not wrong, but some of the argument is not completely justified, and that topological gap was filled in since 1920 by Ostrovsky. And the first complete and rigorous proof appeared in 1906 by this person. And that was the first time the result is extended actually to the complex coefficient, not just the coefficient, real coefficient for the polynomial. That's what happened to the real line. You threw in one imaginary solution to a quadratic equation, something amazing happened. Not just a quadratic, all degree of the polynomial completely factors in this complex system. That does not happen with this Q5. Q5, you throw in imaginary number, root of 2, and it is, we already saw that the 5 here does not have a square root 2, square root, so therefore you have to throw in square root of 5 here as well. But that doesn't still take care of the problem. It's actually far from being algebraically closed. That means it has all the solutions for all the polynomials. So they have to throw in all the more numbers, and more numbers. It becomes a huge field. It's called algebraic closure. So we learned this in an abstract algebra, the formal construction. But once you throw in all the numbers so that it's completely factors, it does not stay as complete. That means in the metric system you will have a problem if there's a sequence that seems like it's approaching somewhere, but that conversion point is not in this algebraic closure. So you have to throw in more numbers to make it complete. So after you complete that, it turns out magically it remains algebraically closed. So we eventually get to a place where it's complete and algebraically closed. So that object is called CP. When we do calculus, especially integration, and sometimes we need to think about this number system to evaluate integrations and stuff like that. I'm planning to give a part 2 of this talk that focuses more on topology and elementary calculus. In this part, we will use a language of real analysis and the calculus.